Thank you for joining ReachMD XM157 for this month's special series, Spotlight on Neurology and Psychiatry.
What does the most recent research tell us about the pathogenesis of Parkinson's disease? You are listening to ReachMD XM157, the channel for medical professionals. Welcome to a special segment on neurology. I am your host, Dr. Mark Nolan Hill, professor of surgery at the Chicago Medical School, and with me today is Dr. William Burke. Dr. Burke is a professor in neurology, an associate professor in medicine and in neurobiology at St. Louis University Health Sciences Center. Welcome, Dr. Burke.
Thank you for having me.
Today we are discussing the latest research on Parkinson's disease and its pathogenesis. Dr. Burke, in the media, the lay public has seen people like Michael J. Fox or Muhammad Ali with the effects of Parkinson's disease. What can you tell us about what's commonly known about the pathogenesis of this disease?
Well, first of all, let me just go through some of the clinical aspects of it, which are, as people have noted, there's a tremor. It's usually a tremor of the hand. It's usually a very coarse tremor. Sometimes it can affect the leg, or sometimes it can affect the head. There's rigidity or stiffness, and there's bradykinesia or slowness in movement, and that slowness can be manifest in the way the person walks, or it could be manifest in the facial expression. There's a decreased facial expression, and there's a tendency to fall because of postural instability. Now, those symptoms are due to loss of a particular subset of nerve cells in the brain. There are over 200 billion nerve cells in the brain, and the area of the brain that's affected in Parkinson's disease, called the substantia nigra, has 400,000 neurons. And the neurons that are affected in Parkinson's are called dopamine neurons. The reason that they're called dopamine neurons is that dopamine is the neurotransmitter. The way the brain works is that each neuron projects onto the other neuron, but it doesn't touch the other neuron. There's a gap in between neurons called a synapse, and they communicate with each other by releasing a chemical transmitter.
Well, what happens in this disease?
What happens in Parkinson's disease is that the dopamine neurons are lost, and there have been a couple of main theories.
What are those, sir?
Is why that these dopamine neurons specifically are lost. There's a lot of neurons, but only the dopamine neurons seem to be selectively affected. And the two theories are, obviously, if dopamine neurons are lost, maybe it has something to do with dopamine. Maybe dopamine is toxic. Well, that was looked into, and it turns out that dopamine isn't very toxic, if toxic at all. And on top of that, there's no genetic link between dopamine and Parkinson's disease. The other main theory is that a protein called alpha-synuclein has been linked to the disease. There's a pathological marker for Parkinson's disease called the Lewy body, and that is made up of an aggregation of alpha-synuclein protein molecules. The other main thing here is that there are mutations in alpha-synuclein that are linked to the disease, so that it's known that alpha-synuclein plays some role in this disease. However, the problem with the alpha-synuclein theory is that alpha-synuclein is not only in every nerve cell, it's in every cell. It's even in the glial cells. So why is it that the dopamine neurons are being selectively affected in Parkinson's disease?
What's so special about dopamine as a neurotransmitter?
Nothing particularly. There's about 50 neurotransmitters in the brain, and dopamine happens to be one of them. But what happens is that dopamine gets converted by an enzyme called monoamine oxidase to a very toxic substance called, the abbreviation is dopal, D-O-P-A-L. And we've been looking at this compound for many years. It's about 400 times more toxic than the dopamine itself. And it's the only breakdown product of dopamine that is toxic. We looked at dopamine, we looked at all the other breakdown products, Dopac, HVA, the other metabolites of dopamine. Only dopal is toxic.
When you mean toxic, you mean toxic to the human?
It's toxic to the nerve cells, It kills nerve cells. No, we don't mean it's toxic to the human. It's made in nerve cells. and it kills nerve cells. We demonstrated this by injecting them into the substantia nigra in rats. We also demonstrated by doing tissue culture experiments in which we take models of dopamine neurons and show that the dopal kills these cells. So it kills dopamine neurons. Well, the thing we're doing in this paper is linking these two theories, the alpha-synuclein theory and the dopamine theory. And what we show in this paper is that dopal triggers the aggregation of alpha-synuclein. When alpha-synuclein aggregates, it becomes toxic. It becomes a toxic oligomer of alpha-synuclein. It makes clusters of alpha-synuclein, and these small clusters can poke holes in things. It can poke holes in the mitochondria, it can poke holes in the storage vesicles, and it can cause release of more dopamine. So what our study does is it shows why dopamine neurons are affected and why alpha-synuclein is also linked to the disease.
If you have just joined us, you are listening to the Clinicians Roundtable on ReachMD XM157. I am your host, Dr. Mark Nolan Hill, and with me today is Dr. William Burke. Dr. Burke is a professor of neurology and associate professor of medicine and neurobiology at St. Louis University Health Sciences Center. Dr. Burke, could you please continue on the research that you are doing in Parkinson's disease?
Well, what this does is it provides a complete explanation of why you get the Lewy body, because we can show that these aggregates in the presence of dopal will form very large aggregates that mimic the Lewy body, which is the pathological marker. It also forms much smaller aggregates called oligomers, which themselves are toxic. And we believe that the toxicity of the alpha-synuclein is mediated at least in part through dopal itself, because dopal, we've shown, can trigger cell death on its own. It doesn't actually need the alpha-synuclein. It can open what they call mitochondrial permeability transition, which is a mechanism for cell death. The mitochondria release a protein, and that triggers a whole cell death mechanism, and dopal can do this just on its own. So what we think is happening in Parkinson's disease, that these two items are interacting. The dopal is triggering the aggregation of the alpha-synuclein, which is releasing more dopamine, gets converted by monoamine oxidase to more dopal, and eventually you build up to a level that becomes toxic.
Now, how can this information that you have learned be clinically correlated and passed on to treatment and understanding of Parkinson's disease?
Well, what this does is it provides a target for therapy. Because we know how dopal kills cells, there's all sorts of targets you can look at. And the first target would be have the cell stop making so much dopal. And one of the ways to do that is to use MAO inhibitors. And actually, some of these MAO inhibitors are already on the market, and they're being used. And there's actually several studies that show that some of these MAO inhibitors are neuroprotective. They delay the progression of the disease. There's pretty strong evidence for that. So that's one way. The other way is there's certain things that happen in Parkinson's brains. For instance, there's an enzyme called coenzyme Q10, and that enzyme is involved in making a cofactor for another enzyme that breaks down the dopal. So there's not as much evidence for this, but people are taking, say, coenzyme Q, and there's at least one study that suggests that it may be neuroprotective, but the evidence is not quite as strong as for the MAO inhibitors.
Years ago, people with Parkinson's disease used to take L-Dopa. Is that still used?
Oh, yes. L-Dopa is the most effective treatment for Parkinson's disease, but it's a symptomatic treatment. It treats the symptoms of Parkinson's disease, which is a very good thing, but it does not prevent cell death. It does not prevent the death of the dopamine neurons. So that's the difference between what we call neuroprotective therapy and symptomatic therapy. The L-Dopa is a very good treatment for Parkinson's disease. It's a precursor for dopamine. That's why it's used. And the reason you use L-Dopa instead of dopamine is that L-Dopa crosses the blood-brain barrier, but dopamine doesn't. So you can take a pill, the L-Dopa goes into the brain, it gets converted to dopamine. So it's still a very good treatment, but it treats only the symptoms, and after about 5 years, it becomes less and less effective. So we need to find something else that will actually slow down the death of these cells to slow down the progression of the disease.
Is Parkinson's disease always progressive?
Yes, it's always progressive. The neurons are dying all the time. So far, other than the MAO inhibitors, which there is, I'd say, fairly good evidence that it may slow down this progression, these neurons will keep dying. As a matter of fact, you have to lose 70 or 80% of your dopamine neurons before you even get the symptoms. So by the time somebody gets symptoms of Parkinson's disease, they've lost quite a number of their dopamine neurons already.
What's the purpose of some of the surgical intervention for Parkinson's disease?
The surgical interventions are mainly against some of the long-term side effects of L-DOPA. You get dyskinesias, you get excess movements with L-DOPA. After a while, the receptors become super sensitive. And basically, the surgery in people who qualify for that, it decreases the requirements for L-DOPA and it decreases these abnormal movements as the side effects of long-term L-DOPA.
Generally speaking, the progression of this disease, is it rapid or is it slow?
It's pretty slow. I mean, people on L-DOPA can go 3-5 years without too much problem, and then they eventually get more and more problem. They get more problem with their walking, more problem with their speech. They may start to get trouble with swallowing. I mean, you can live a normal or even super normal life and still have Parkinson's. For instance, Pope John Paul died at age 85 of Parkinson's disease. So, I mean, that's more than the average lifespan. So it doesn't necessarily directly kill the person, but it makes the quality of life decrease as you get older and older.
Finally, Dr. Burke, looking in your crystal ball with respect to your own research and other research, where do you see Parkinson's disease 5, 10, 15 years from now?
I hope that we have something that will stop the progression of the disease and that they will be able to diagnose it very, very early, even before the symptoms come on, so that somebody could be given a pill and they won't progress at all and they'll live a normal life and they won't have the complications of Parkinson's disease.
I want to thank Dr. William Burke, who has been our guest. We have been discussing the latest research on Parkinson's disease. I'm Dr. Mark Nolan Hill, and you have been listening to the Clinicians Roundtable on ReachMD XM157, the channel for medical professionals. Be sure to check out our website at www.reachmd.com, which now features on-demand podcasts of our entire library. For comments and questions, please send your email to xm@reachmd.com. And thank you for listening.
Listen all month as ReachMD XM157, the channel for medical professionals, features a special series, Spotlight on Neurology and Psychiatry.